Let's talk about NAT servers next. The core idea adopted by NAT is internal private network, external public network. We just said a kind of NAT, called static NAT. The public network and the private network are actually two-way. But when we go to use dynamic NAT and PAT, actually, our traffic is only from intranet to extranet. Then the external network replies with the packet. Because when we go out online, a mapping table will be formed on this device. After the data goes out, when this traffic comes back in the future, it has to look up the meter. If there is this mapping entry in the table, it can be converted back towards. If there is no traffic, there is no return. It means, if you use this way, you are directly on the public network. Use 100.1.1.1 to access the private network. You cannot access this device, because it is a private address, even if you can find a device like it. But since this data just didn't access you internally, it does not have this mapping in its mapping table. Even if your data arrives on this device, since it cannot find a corresponding mapping, it cannot reply to the server. But sometimes, when you are working on a project, often found, now a client, originally, an internal server was an intranet server. But now maybe the company has grown in size. Hopefully this internal server also provides some access to the outside world. So what should I do? There is no direct access to a server on the public network, because the server itself is an accessed end. It does not actively generate traffic. It will not access other devices on the public network. It is only accessed. We can do a mapping here. For example, I configure the NAT server on this device. If it accesses a certain port on this device in the future, it can jump to a certain port of the internal server, and then let it access, which is equivalent to NAT server can realize this requirement. But all you need to configure is, you put the service on a certain port of the internal server, a service converted to this address on the public network, and then publish it externally. Then others will be able to visit in the future, because we can reach a public network address on the public network. You can access the corresponding service on this public network address. As a company device, it can be configured. If other devices access its services, it can transfer the traffic to the downlink server. Then you can access it accordingly. To be honest, still want to access the public network. This needs to be configured accordingly on this router. Some friends may find this too troublesome. You have to configure one by one. Yes, because your company will not have so many servers waiting to be accessed by others. Usually, if we have one device, we just need to configure one. The specific scene is different. Like the daily employees in the company. There are many people who use the internet. There are only a few configurations for the server. That's it for a small company. Let's talk about its configuration. We still focus on configuration. It is a configuration. After watching, let's explain. Very simple. This is the reason why I want to simulate a router on the PC. I want to wait to mock a service. Simulate a telnet service on the PC. I want to enable telnet on the PC. There is a command that is the line. Then set up a virtual terminal link. VTY. Set user 0 to 4. This is when we talked about configuration before. Earliest configuration. Password Cisco. Transport input telnet. I am now on. PC1 is allowed to be telnet. Telnet is port 23. I hope now the traffic on the public network can be transmitted from this device in the future to access the telnet service in OC1. As just said, I should configure it on the gateway device. Let's look directly at the command. IP NAT inside source. It is a static. We want to enter one by one. Then enter the question mark. We are now accessing the telnet service. Then it is based on port 23 of the TCP protocol. The TCP protocol at the transport layer is used. I now want to internal this 192.168.1.10. It's port 23. That is the telnet service. Future mapping is 100.1.1.1. A port 23 of the public network outbound interface. Let me explain this sentence. If it is set internally now, later, then you will find. Now if it accesses port 23 of 100.1.1.1 on this public network, that is, it telnet this interface address. Then the gateway will be mapped to port 23 of the internal 192.168.1.10. The gateway will forward the traffic down. Let it access port 23 of the PC connected to the gateway. That is, it telnet is this device. But it can log on to PC1. We'll wait for a verification. Because if in this telnet 100.1.1.1, then enter the gateway, it proves that the login failed now. If log on to PC, it proves that our mapping is successful. We can do experiments to verify. But I tell you, we usually don't enter 23 here. Because we usually do not configure the internal and external ports to be consistent. For example, now it telnet this address. And found. Telnet this address is really telnet to a device inside it. It's not very safe. It found that port 23 is open. It can telnet. It actually logged on to a server inside the company. It's relatively dangerous. We generally don't do source port mapping. We usually make a modification outside. For example, mapped to external 10,000 ports. We press enter. Now that we have configured, let's look at a more important thing first. It is the NAT table. You will find, now that I have finished typing, there will be such a mapping in the NAT table. The internal 1.10 port 23 is mapped to the 10,000 port of 100.1.1.1 on the public network. Is now a static mapping. Only static. You can directly see it in the mapping table after inputting. If dynamic, you have to have traffic access to see. Then let's come to the operator to test it now. We are going to telnet. Telnet 100.1.1.1. I won't press enter now. Because it won't hold down. Because telnet is not accessing 100.1.1.1 now. Instead, the 10,000 must be added later. Actually, I am accessing this port. Then came in. I telnet from the operator here is the 10,000 port of 100.1.1.1. I'm here on PC1. So saying this mapping means something like this. Publication. Now a server inside. You only need to access this interface. Access port 10,000 of this address. Then it can log into the internal server. Externally, the company's internal server is this address. But actually it's not. So it is equivalent to. It can protect the private address of the internal whole. Secondly, as a private address, corresponding access to traffic on the external public network. This is also what NAT can do. And NAT is at the beginning of the overall design. It's not for online use. NAT was originally a security method. I give a simple example. For example, this is an intranet. This is also an intranet. They will have some business dealings in the future. When you have business dealings, you must communicate. There may be some traffic exposure problems in communication. For example, the address may be leaked. We don't want other people's addresses to appear in their respective internet segments. I also don't want my address to be exposed. Usually say, we scrub the address. It is to convert NAT between both sides of the export. Then make a fake address. Communicate with each other. This also works. Does not affect business traffic. But no one can get the specific device and address of both parties. Okay. The above part is NAT. Finally, before we talk about the experiment, let me first give a brief introduction to this SDN. To be honest, we must not understand this thing when we learn it in the NA stage. But the outline has. We have to talk about it. Actually, a lot of knowledge in the courseware is too difficult for now. I will pick some that I think everyone can accept at this stage. Before I talk, I will open the experimental environment. Otherwise, the device will start too slowly. This is a small exercise at the end of the class. It's not that difficult. We are just doing a more comprehensive exercise. SDN is called Software Defined Network. What we have learned before is actually decades-old technology. E.g. OSPF, VLAN, EIGRP etc. As old technology. Many devices support these technologies. Manufacturers can't keep pushing the old and bringing forth the new. Otherwise, there will be no money. So actually for SDN, it is both a new type of solution. It is another trendy learning direction, so to speak. Because the entire internet actually follows the manufacturers. Let me briefly introduce the usefulness of SDN. It can solve some common problems in our daily network. First of all, we need to know some disadvantages of the traditional network. The first is called purely distributed. Pure distribution is, for example, I now have some equipment. I want to realize that two terminals can be interconnected. Then I need to run OSPF on these devices. Announce each other after running. To configure the interface address. Modify the device name. Then run OSPF. The announcement is to synchronize the routing table between devices. In order to allow this network segment and this network segment to be learned by all devices. Then let them both communicate. We just demonstrated a configuration like this today. So you will find, when facing networking in the future, only a few devices are fine. If there are many devices, you have to configure accordingly every time. Independent configuration for each device. Especially for projects. Of course, we now also have Gambit for Python automation. So this thing is not so absolute. But it is still somewhat different from the technology in SDN. Let's talk about automated opening. In fact, it is just some automatic configuration for the device. SDN is more advanced than that. Let's not talk about anything else. What about standalone configurations? This is a disadvantage now. Secondly, from the control level, each device is required to calculate independently. Actually, the device has two actions. The first is called data forwarding. The second is called calculation of data. Devices run OSPF on each other. Synchronize routes with each other. Its action on the routing table is called calculation. A router has many interfaces. A data comes in from an interface. The device queries the routing table for data forwarding. This process is called forwarding. So actually, forwarding and computing are two actions. But it's all done by the router. It is called each device to calculate independently. So, although the router performs data forwarding, but it needs to maintain its own routing table. You have to exchange messages every day. Take care of the neighbors. If not, the device has to recalculate, plan the route, switch some ready lines, etc. These are calculations. For example, there are now multiple paths to the same destination. Specifically, go up, step down, still going. This also needs to be calculated. So it's all called computing. After the calculation is completed, the table can be forwarded. Let's go on. Outdated software features without innovation. Multi-brand incompatible. Actually, it means you can summarize EIGRP in one sentence. For Cisco, this thing is much easier to talk about. You will find that EIGRP has almost no scenarios to use now, except for some relatively small-scale commercial banks of a local nature. They are not regulated by the government, and is joint stock. Relatively rich Cisco equipment can use EIGRP because neighbors converge quickly. Doesn't need to be as slow as OSPF. Indeed, there are such, but rarely. Like some proprietary technologies in other manufacturers, such as hybrid. It's like a policy based on VLAN. The traditional VLAN is the same VLAN can communicate. Different VLANs cannot communicate. Different VLANs have to cross 3 layers to communicate. Not on the second floor. Hybrid can do it. Layer 2 communication between different VLANs can also be completed. It is equivalent to a strategy. But hybrid will only be used in Huawei. For example, voice VLAN. Few other scenes. These techniques are good because it is a proprietary technology. There is no way to ensure that all equipment from various manufacturers is combined in large projects, so no one uses. For example, others can use EIGRP, but we can only use OSPF. Then we don't use this EIGRP. I will not go to buy equipment that can use EIGRP. Its Cisco equipment is more expensive. We are all economical networking, subject to the current conditions. The cheaper the better. Then the cheaper. We require equipment to use more public technology. Then it reverses and makes manufacturers unwilling to research new private technologies. Manufacturers have spent a lot of research and development funds for decades. Launched a technology such as EIGRP. The development cycle is quite long. After it was launched, no one used it. The money is wasted, including software feature incompatibility. In fact, it's all one meaning. It's because of brand incompatibility. We have been using public technology over time. Now there is no manufacturer to do private technology. Everyone likes to study hardware. Everybody knows. Proprietary technology has only 2 outcomes. The first is to be stolen. The second is useless. So it's not worth it. Manufacturers are also profit-seeking. Must put the economy first. Now we won't be developing proprietary technology anymore. You will find many factors combined. As a result, the advancement of traditional networks is very slow, because there is no new technology. So SDN appeared. It is specially designed to solve the problems we just mentioned. SDN first makes a point. Forwarding control separation. Control is really computing. It is the calculation I just told you. It actually means forwarding control separation is make a distinction between forwarding and control. Retweet is retweet. Calculation is calculation. As a router, in the future, it does not need to calculate the routing table by itself to complete data forwarding. It is only responsible for forwarding. We introduce a device across the network. Controller hardware called SDN. It is responsible for calculating. After it completes the calculation, it sends the table directly to the device. This table is more than just a routing table. For example, you will learn the label in the future. It can also calculate. After it's over, directly forward the generated table to the device. The device gets this table and forwards it directly. As a router, it does not need to support OSPF anymore, because it supports OSPF in order to establish neighbor synchronization routing table. Now the table has been directly made to it by the SDN controller hardware. It does not need to support OSPF anymore. It is equivalent to the separation of forwarding and control. Everything a router needs to forward. After the SDN controller hardware is calculated, give it. Then the data is sent. It directly performs lookup table forwarding. No more calculations. This way for downstream equipment, they become a transponder. That is, into a transponder called a white box device. All control is done by devices such as the upper layer SDN. These downstream devices only need to perform table lookup and forwarding. Centralized control from one device. All downstream devices only need to complete the forwarding. Finally, the separation of forwarding and control can be realized. Let's simply draw a picture. Assuming this is the controller hardware for SDN. These are routers one by one. The original router had to run the protocol. You have to configure the address yourself. Don't bother. Now these devices, as long as SDN is supported, it is the SDN controller. The device can automatically find the SDN controller when it is turned on. Then it sends the configuration template to the device. The device does not need to be configured by itself. Do some corresponding configuration on the SDN controller. It can send down the appearance. Whether it is some basic configuration of the device, or a semblance of the future of computing, forwarded directly. The equipment below does not need to do anything. The advantage of this is maximize the reduction of some calculations of downstream equipment. Save hardware resources. The downstream device does not need to open the routing protocol anymore. The cost of equipment is reduced, because there is no need to buy high-end equipment. Okay. Let's talk about centralized control. One controller hardware can be centrally controlled. It can not only control the router, as long as the device supports SDN. Whether it is a switch, or router, or firewall, everything is possible. Wireless AP can support, as long as the device supports SDN, can be controlled by the SDN controller accordingly. The last one is called Open Interface. Now say that everyone may not fully understand. Let me talk about the meaning of Open Interface. It's like a platform. The platform is like an app store on your mobile phone now. What service do you need to go in and download? For example, in college, I am a network engineering major. Many of my classmates are engaged in game development. They develop their own games, and then upload it to the App Store. Play for free. It's a graduation project. So this kind of thing is equivalent to a platform. You can upload your own work. Certainly. It can also be paid. If anyone wants to play, he wants to pay to download the game. You'll be able to reap the benefits. In short, others have to pay to use this feature. We are talking about the same. In terms of the entire device now. Vendor equipment has outdated functions and no innovation. It does not matter. I now open the interface to it. Many people can come in and develop. Not only Cisco. Many other manufacturers can come in and develop. Only need to develop these functions. Upload to this platform now. Upload to such an interface. Can be used by others for a fee. It's like a store. The SDN controller has a hardware in the web. Everyone can see the interface intuitively. This thing doesn't look like that on the command line. No need. We have a graphical interface. Can come in for development. We call it support for third-party development. Equivalent to accessing more developers. Opened up. Now if the user wants to use, you can spend money to buy this device. Please note, its difference is, originally only Cisco devices supported EIGRP. Now this device supports SDN. Then open the corresponding port on the SDN controller hardware. All these services developed throughout the platform in the future. As long as the device supports SDN now, can be downloaded and used. It is not required to be a device of a certain manufacturer. But not yet. For now, Cisco's SDN hardware can only control Cisco's. So, there is no real implementation of such a form. Not really open up. Some people may think, isn't this equivalent to letting yourself spend money in disguise? Actually not. Like some functions you use on the device now, also have to buy a license. In the future, these functions are just another way. Then let you pay to use it. It prevents multi-vendor incompatibilities. You will find SDN is facing the current stage. SDN that most students come into contact with. In fact, they all refer to the control hardware of enterprise-level SDN. These functions in the SDN that I just talked about. In fact, it is not the core function of SDN. Only when you get the IE stage can you know its core functions. Now I can only tell you. There are actually quite a lot of things we can understand at this stage. Let's talk about its development. The beginnings of SDN are open source. It was started based on the Linux system. This is an open source system. Supports secondary development. It was originally a professor at Stanford. In order to solve the problem of complex network and high cost of the current project, developed a system. Notice, it develops a system. It is a software. Developed an SDN controller system. This is a software. It doesn't sell hardware. This is free software. This system can be installed on an ordinary server. Install on normal PC. Install on cloud server. All okay. It can be used as a core node of network management. No matter where it is installed. This device is a core node. These downstream devices only need to support SDN. Like I said, this can be controlled accordingly. This saves the business money. The following equipment does not need to buy such high-end equipment. All you need is a device to do the calculations. Although the idea is good, but no manufacturer is willing. You now hope that the underlying device does not need to calculate. It's all white box. Manufacturers are now developing so many high-end devices that they cannot sell them. So in fact you will find it is not so simple from the perspective of technology development. Often there will be more in-depth content. To us. Now we have two organizations. One is called ONF. They develop systems like ONOS. It is more compatible with operators. That is, specifically for carrier networks. Then the software developed by ODL is also called ODL. They are geared toward data centers and enterprises. It is more of the current networking architecture. Into two directions. In fact, they get a lot of support. Especially like ONOS. Actually, they have a lot of support from operators. Because for operators, I have to buy a lot of equipment from manufacturers every year. So they are kind of very ambiguous relationship. Just a good relationship. But in fact, they are also a relationship between paying and being paid. So they also want to save money. To put it bluntly, the operator has a lot of things. Hope to save money. If so, the equipment they buy every year does not need to be so high-end. This saves a considerable amount of money. So we will support accordingly. But I also said, vendors certainly don't need to see open source. All devices are now available for the entire market. Everyone does not buy high-end equipment. What about our equipment? But now organizations are starting to develop such technology. The manufacturer also has to develop. If the new generation of technology in the future is getting stronger and stronger, so as the world's two largest manufacturers, they must want to stand on the wind. That is, the development of technology cannot be truly stopped. What they can do is invest. They will also invest in organizations like, for manufacturers, the investment in ODL is significant. For operators, investment in ONF is significant. For this organization, many manufacturers are investing in. For such an organization, they get a lot of investment. Including now if you want to download. It can also be downloaded directly to their official website. With controller. After downloading, can be installed in a virtual machine. But it's useless. Because you can't control the device. No device is compatible with them. So I gave up completely. When manufacturers invest in, will also wait and see while investing. And develop their own technology. Let's talk about DNAC next. Called DNA Center. This is Cisco's main control hardware product. Now a device like this. It is more about the support for Cisco's SDN equipment. Actually, for you at this stage. First of all, I can't understand. Secondly, there are no scenes to give you some corresponding explanations. But I can tell you a few functions inside. Some friends may feel a little puzzled. Since they don't want to develop. Why are you pushing your own product now? Because they are investing now. To invest is to become a shareholder. Technology itself can be shared by everyone. It is not shared. But many core technologies have actually been obtained. And there are also core personnel to learn from. So you will find, after the investment is completed, the overall routine manufacturers there are already clear. Then they can start investing in their own products in the market. Cisco didn't sell hardware in the first place. It sells software. Called APIC-EM. They don't just sell this. They push a free software like a public beta version for users to use. See how the market accepts it. If the market feedback is good, then put together software like this. Sell with hardware. There is now a piece of hardware. Support software functions. And tell the user. They have some new features. If the user feels okay, we'll buy their hardware. Let me briefly talk about a few functions here. The first one is SD access. Software-defined access. In this future you get the data center environment. To really feel what it means. I-WAN is now called SD-WAN. SD-WAN was previously called Wisdom Wide Area Network. Now it's called Software-Defined Wide Area Network. It can be done in some large networks. Some traffic load on egress. For example, engine room, bank etc. Including special projects we will handle in the future. And our daily traffic export are capable of loading. Is quite powerful. But now for businesses. These things are not used in the enterprise. So let's talk about some things in the enterprise that are helpful to everyone now. Let's talk about this base automation first. It means the upper device automatically sends the configuration. The following equipment automatically completes the automated deployment. It's called automation. Then plug and play. Automation goes online. For example, there are a lot of smart speakers now. Once connected to the internet, it can talk to you. This is called automation. The router automatically connects to the network. It finds the SDN controller by itself. The SDN controller reversely controls the downstream equipment. Start delivering fixed configuration. It's called plug and play. You don't need to configure it anymore. Look down. Monitoring and troubleshooting. Monitor the health status of some devices in the current network. For example, device CPU usage, fan operation, etc. Give appropriate diagnostic opinion. That is, now there is no need to set up network monitoring for that fee-based service. No need to buy now. SDN controller hardware can give you monitoring. Monitor interface bandwidth, CPU usage, memory, fan, device log, provide you with corresponding alarms, etc. It's all okay. Look down. There is one called EasyQoS. Simple quality of service. That is, do some network optimization of the network. Speed limit. Congestion avoidance. These corresponding functions can also support. Look down. Assurance. It is different from the monitoring and troubleshooting we just mentioned. Troubleshooting is generating errors and telling you why. Then give you the solution. Prevention means you haven't had a problem yet, but due to the powerful database matching in the background, then it thinks you might have a problem now. Give you an early warning. Let me give you an example. You keep your head down playing with your phone. The face is very close to the phone. Then you are probably nearsighted. If you have been close to your phone for a long time, then this controller will tell you. If you go on like this, you will be nearsighted. For example, how hot is the fan now? How much has the CPU reached? How much memory? The possible consequences of going out now. That's what I mean. It hasn't happened yet, but I told you first. This is what a powerful database can do now. What I said above are not the core skills of SDN. The core skills are the first two. Let me tell you again. The first two are actually aimed at the current changes to the networking architecture of the campus network. Because now it is tube-well structure. Now in the entire data center. Using a two-tier architecture. Backbone separation. Then SD access is actually aimed at the two-tier architecture. Not a traditional three-tier network. The three-tier is what I call the three-tier architecture. So, it is not a technology used in corporate networks. Secondly, for SD-WAN, it is more for some debugging of export devices. Devices that can be connected to the external WAN at the egress. Implement some intelligent traffic load. Real-time switchover for some failures. Diagnosis, etc. It can do better support. For both SD-WAN and SD access. There are a lot of small knowledge points in it. No instructions given here. Specific to IE we'll talk about. The premise is that you have to learn every function in it first, in order to know what functions it is composed of. All basic technologies for non-enterprise networks. In fact, it was not mentioned in the NA stage. So everyone can't understand this thing at this stage. In the NA stage, everyone should first understand the entire SDN. Where can it ultimately be regulated accordingly? Let's just look at the page. This is called big data analysis. All these controls inside, we can all debug in the form of a web page. That is, For future configuration devices, you configure less. Now each device is configured. There are two ways of external interface and command line. Overall, in the future, SDN will be more debugging based on web pages. You can go to change and view the device parameters, including delivery time, control access, set password, certification, etc. These can all be done on the device. The following is the analysis architecture of some campus networks. These slowly everyone learns the structure to know. Here are some of its insight assurance capabilities. In fact, the functions of many projects can be done now. Okay. We are finally entering the part that you may be most looking forward to. It is equivalent to making a simple summary of the current stage. I will talk about this experiment next. Let's do a review of the previous course content. Then configure the experiment by the way. I'll turn on the device first. Let's analyze the topic first. In this topic are some configurations we learned throughout the NA phase. Basically all have been checked. Although there are not many equipment. But there are a lot of things to check. Let's take a look. First of all, there are 5 routers in the whole picture. 2 PCs. A switch. We're going to configure it. PC 1 writes 192.168.1.x here. Then it will not manually configure the address. Let it fetch automatically. We configure PC 2 manually. A 2.0 network segment is configured. They are not in the same network segment. Secondly, we configure subinterfaces here on the gateway. We do one-arm routing. Everyone should be able to see. Now the 2 devices cross the network segment. Since this is the case, it is to let everyone do one-arm routing. Connected to the router. We up subinterface here. This is the configuration we talked about before. We want to be on the gateway device. Also enable DHCP. Since this we have manually configured. It does not need to issue IP. Let it issue a fixed IP address to PC1 forever. Is 192.168.1.11. Issue a fixed IP for a fixed MAC. This is what we said before. Then on this device, do network address port translation PAT. Use this outgoing interface to do. Devices inside the future want to go online. This is the NAT we just talked about. We use this way of network address port translation. Point the traffic out. Further down, we want to run OSPF on the R1, R2, R3, R4 device. R1 and R2 each enable a loopback port. 1.1, 2.2, 32-bit mask. Notice 1.1 as a circle. This address can telnet this 2.2. But can't ping 2.2. We just demonstrated the ACL. In fact, it is just a ban on ping. But how can we achieve telnet but not ping? Let's wait for the demo. Look down. In the future, this 1.1 will go to this 2.2. Traffic to be sent. I hope that when the traffic passes, it goes down. When the traffic comes back, it goes up. Actually, these two are equivalent. We need to modify its path. That is, need to modify its orientation. I want the traffic to always come like this. The last one. We can only use one static route. In fact, when we do targeted ACL, for a variety of scenarios, sometimes people mess with static. So we have to stipulate. If only one static. We should write this statically here. Write a default route to the public network. So other places. We won't do too many operations anymore. Then we will start the formal configuration. We start the configuration from the switch. We must first enter the configuration mode. Let's rename the switch. Then assign VLAN to it. VLAN 10. Then VLAN 20. After the VLAN is divided, we're going to configure them accordingly. Let's do a simple plan. This is VLAN 10 on the left. On the right is VLAN 20. So we enter the corresponding interface. Interface E01. Switch port mode access. Switch port access VLAN 10. Then we enter the E02 interface of the switch. That is 02 interface belonging to PC2. Switch port mode access. Then assign VLAN to it. Switch port access VLAN 20. Okay. It's not working now. Certainly. The PC has not configured the address yet. We first configure the switch. Go to the interface where the switch is connected to the gateway. This is the 00 interface. Interface 00. After coming in, before we enter switch port mode trunk, have to enter another command first. I mentioned it in class before. It may not be possible to directly enter the trunk, because we have to modify its encapsulation mode first. Change it to .1Q. Then, switch port mode trunk. It entered smoothly. Next, we are going to release the corresponding traffic. Switch port trunk allowed VLAN. We're going to pass 10 and 20. After releasing the traffic, we can look at the configuration. Do show run interface. Let's take a look at the configuration under the 00 interface. We first changed its encapsulation mode here, because the default is ISL. Cisco proprietary. We're going to make it public. But I also told everyone. For many devices in the real network now, many Cisco devices are now .1Q by default. For some devices, you don't need to enter. But some old devices have to enter this command. Then go to modify the trunk mode. Allow VLAN 10 and 20. Change the mode to trunk. Okay. I'm done with the configuration of the switch. Let's go to the gateway to configure it next. Other equipment comes first. To save time in class, I have finished configuring the interconnection interfaces of R1, R2, R3, and R4. I won't configure the address in class for a while. You can configure it yourself after class. Let's change the name. It is Gateway. So now I'm going to configure one-arm routing. Gateway configuration one-arm routing. The first step should be no shutdown. First you have to open this interface. Otherwise, there is no way to configure it with a single arm. After the interface is opened, let's go to the sub-interface. Interface Ethernet 00. We enter VLAN 10s. This .10 is not its processing capacity for VLAN 10 is identified here. It doesn't matter how many are here. But usually this sub-interface is for which VLAN service. We enter the corresponding number. The sub-interface is now serving VLAN 10. We will enter 10. We now modify its schema. Give it the ability to handle VLAN 10. If there is data coming in from the future sub-interface, it will tear down this VLAN 10. If there is data, it will be tagged with VLAN 10. This is what we said before. Then configure the address for it. Its address is the gateway of PC1. PC1 is 1.0. Then we configure its address. 192.168.1.1. 3255 and 10. This is what we call a sub-interface. Then go to another interface. Interface Ethernet 00.20. For VLAN 20 service. Still change it to .1Q first. .1Q20. This command makes it capable of processing VLAN 20. The IP address is 192.168.2.1. 3255 and 10. No shutdown. Open the interface. We have now configured the internal interface. Use two sub-interface addresses. And the physical interface is opened. It just works. We are now going to engage in the external network interface. E01 interface. Interface E01. Then configure the address. IP address 10.0.1.1. Followed by a mask of 30 bits. 255.255.255.252. No shutdown. Open this interface. Then we need to configure the interfaces of R1, R2, R3, R4. I configured it in advance. But I don't know if it is configured correctly. Let's take a look together. On R1 this. Show IP interface brief. Let's check. Avoid configuration failure for a while. I just take a look at each one. Move on to the next device. Show IP interface brief. This is right. Then R3. I will not demonstrate the interface address to you in class. This is what I have already configured in advance. There's nothing to say about this. Just configure one by one. Last R4. It's okay. Now the internet address is configured. I have also used the loopback port addresses on R1 and R2. So what are we going to do now? Look. PC1 has not done automatic address acquisition. We did not manually configure the address of PC2. We just let the VLANs PC1 and PC2 belong to be divided on the switch. Then the switch is configured with the gateway. Configured the section about one-arm routing. Interconnected interfaces are configured with. Then the internet routing of the external network is configured. Then let's start configuring one by one. Let's let this PC1 get a fixed IP address forever. 192.168.1.11. Show IP. We can see the MAC. Then we need to copy this MAC here. Then to the gateway. Because we want to configure the gateway as a DHCP server. IP DHCP pool. We define an address pool. Suppose this address is called P1. We are now going to assign an address to a single host. Then I just enter host here. Because I only configure for one host now. Configuration address. 192.168.1.11. 24-bit mask. After adding a fixed IP and mask. Set up the corresponding gateway. Gateway is 192.168.1.1. Because they have to be 1.0 network segment. So it belongs to VLAN 10. After that set DNS. DNS server. 114.114.114.114. Okay. We are now done setting up DNS. After setting. We are about to bind the address. Client identifier. I'm going to tether the MAC now. I just finished copying the MAC. Paste it right now. We can't just press enter. To add 01 at the front. 01 stands for Ethernet. After that, it must be separated by 4 digits in the form of a decimal point. Then press enter. Now for a MAC address like this. I configured it with a fixed IP address. Gateway gave it. DNS gives it. It itself is a DNS server. It now only needs to open the DNS service request on the PC. So we come to PC1 here. IP DHCP. Then press enter. Start sending out messages. Now if you get the address. It is the address of 192.168.1.11. Gateway is 192.168.1.1. Then PC1 is configured. We now manually configure the address for PC2. 192.168.2.2. 24-bit mask. Gateway is 192.168.2.1. It is now configured. I now ask you a question. If now PC1 ping PC2, can you get through? 192.168.1.11 ping 192.168.2.2. It worked. Let's review the whole process. How is the single arm achieved? PC1 is the address of 1.11. PC2 is the address of 2.2. Cross-network segment access to find a gateway. The gateway is the subinterface of E00.10. 192.168.1.1. Come in interface. Then in the process of coming in, I will put VLAN tag 10 on this interface. When this interface is released, enter the subinterface 00.10 with tag 10. Because it strips the VLAN tag on the incoming interface of VLAN 10. So it will carry an empty label into the router. The router looks at you to go to 2.2. We'll see if there is a local route to go here. There is a direct connection. Come out from its 0.20 interface. Then when the data empty label wants to leave the 0.20 subinterface, it will mark this data with VLAN tag 20. Keep going down. Reserve the mark through this trunk. Then when passing through the access interface, strip off VLAN 20. Then a blank data frame is sent to PC2. The two of them will pass. This is one-arm routing. VLAN Layer 3 communication. This is the VLAN we talked about earlier. We're going to do PAT now. In fact, we just finished talking about this. We first match the traffic of the PC. Because 1 is in the 1.0 network segment. 1 is the 2.0 network segment. So we simply match all. Anyway, it is also the host of the intranet. I want them online now. Permit any IP NAT inside source. This is the fixed configuration format. Must remember. List 10. Associated with this anti-control list. Interface Ethernet 01. Then overload. Port multiplexing. The two ports have not been configured. First enter the E01 interface. It is IP NAT outside. I'm stuck in this link for a while. I think it might be a mirroring problem. Wait a while. In the process of waiting, let's analyze the configuration we will do next. We will then declare OSPF on the 4 devices. After the declaration is over, we can communicate with each other. How can we test that PC1 can access the internet? PC1 can access R1. It can go online. So wait a minute, we're going to do this 1.1. Telnet back and forth. Including PC access 2.2 where to go. In fact, I tell you this. For PC, traffic may not be able to see where it goes. But we can. Let R1 use this 1.1 as a simulated flow. Actually, that is, R1 is connected to a 1.0 network segment. You can simulate it as a PC. Anyway, the future flow will go like this. So we have many ways to verify. Okay. Enter the 00 interface. It is IP NAT inside. We are now configured. Now if configured like this, do you think it will work? Whether it can pass or not. We have a configuration that did not do. I have a default route that is not configured. I want my PC to go online now. Assuming let it go on this R1. For example, I let it ping the R1 interface. In short, this is an external address. Ping 10.0.1.2. Now, first of all, there must be a route pointing out. IP route 0.0.0.0. 0.0.0.0. A default route points to 10.0.1.2. Then let's analyze. I have done what configuration? NAT already done. The internal and external interfaces match. Then turn it into an outgoing interface. Turn with the port. This also configures. The access list matches the PC traffic. Released any. Refers to the default route. Then it stands to reason. If the PC wants to ping this interface now, just visit the R3 interface of the public network. Can it be pinged? You can think about it. I will ping now. Ping 10.0.1.2. No pass. Why didn't it work? Is there a problem with our configuration? Okay. We need to enter the subinterface. If you configure the subinterface here in the future, then actually, when you are going to configure the internal network interface, you have to enter the subinterface instead of the physical interface. When we typed inside just now, it is input under the 00 interface. But you don't need to cancel this order. You can go directly to the internal network interface. Interface E0 0.10. IP NAT inside. Go to 00.20. IP NAT inside. This is the configuration. After configuration, we also go back to PC1. Let's ping again. It works. The reason why I will tell you about the combination of one-arm routing. Just to draw your attention to this. Which interface address configuration takes effect? Actually, you need to configure it accordingly. Let's try it here on PC2. Ping 10.0.1.2. Okay. Also works. That is equivalent to the first two steps and we are done. PC1 automatically obtains the address. PC2 manually configures the address. Get fixed address. Configure subinterface. And then do address translation. Realize that the address of the Internet private network can communicate with the outside world. That's all we've done. We can also verify. Show IP NAT translation. We just sent a lot of pings. Then here you will find 2.2 there are 5 ICMP packets sent out. Local 5 mapping entries. Each time is a random high port locally. A port mapped to the outside world at 10.0.1.1. This is for PC2. The above 5 data packets belong to PC1. A total of 10 packets. Because each is pinged 5 times. Each is 5 ports. So our daily communication consumes a lot of ports. Everyone should know this. Let's go on to configure. Next is OSPF. Now the static line of the whole network has been configured. Configured on the gateway. Pointed to a static route out. Therefore, we cannot configure static access to the external network. It is impossible to write a static point to the private network. This can only be used on the default route. Now PC1 and PC2 can ping the addresses on the public network. That's like being able to go online. Let's start to do OSPF. Enter OSPF configuration mode. Router OSPF. Let's say this is 100. Then press enter. We configure the complete. Router ID 1.1.1.1 will be configured like this. In dotted decimal. Then declare. Network 14.1.1.0. 0.0.0.255. Declare into area 0. R1 also declares network segment 13. Network 13.1.1.0. 0.0.0.255. Area 0. The last one announces the loopback address. Network 1.1.1.1. R2 is the same. Router OSPF 100. Router ID 2.2.2.2. Then we start the declaration here. Network 24.1.1.0. This is the anti-mask. This is not a wildcard. Network 23.1.1.0. Last one. Network 2.2.2.2. We then configure. Router ID 3.3.3.3. Then we declare. This announcement is less. Network 13.1.1.0. Network 23.1.1.0. This is the last device. Router OSPF 100. Router ID 4.4.4.4. Network 14.1.1.0. Network 24.1.1.0. Okay. We are done with this configuration. Let's give it a little time to learn now. I think I should have learned almost. Let's look at the routing table. Show IP route. Let's take a look. Now R1, R2, R3, R4 enables OSPF and is done. 1.1 can tell NAT 2.2 but not ping 2.2. The loopback port on R1 can tell NAT the loopback port on R2. But can't ping. Let's do this last configuration. Let's do this routing first. PC access 2.2 goes down when it goes. Walk up when you come back. This is not easy to verify. We only need to modify the corresponding path. We can look at its routing table on R1. In short, no matter whose traffic goes to R1, R1 must look up the table and forward. Just go to visit 2.2 now. Data here. In fact, it looks at its watch. So it looks at the current table. When going to 2.2, do you go down or up? When including future reply packets, does it go up or down? We are now on R1 to see. It goes 2.2 both up and down. It's loaded. Now there are two lines. Then we will continue to check on R2. Show IP route. For R2, going to 1.1 also loads. If it goes to 2.2 in the future, it is not sure that it can go down. It's loaded. So for now, it can't be sure to go down. Then you can't go back. Because it can be seen from this that R1 is also 2. So we're going to modify. Influence their routing. Modify cost. We talked about how OSPF affects routing. Let's review again. I want R1 to go down to 2.2 now. So let's take a look at how its cost is calculated. This 110 is its administrative distance. We won't talk about this. How did this 21 come out? The default cost of a loopback port address on R2 is 1. Like walking here. Inbound direction of route convergence. This interface is 10. This interface is 10. In Cisco, by default this is a 10M interface. Then its cost is 10. So it is 21 calculated from 1 plus 10 plus 10. If we want to influence routing now, we sure want it to go down when it goes. That is, Next hop is 13. I have to increase the cost on the road of 14.1.1.4. Make it greater than 21. I told you when I was calculating. We need to change the loopback port. We will not change the loopback port today. Let's change the physical port. Because it was shown before. Let's demonstrate a different. Usually, we changed the loopback port on the project to be more. But the future is not certain. If OSPF has many paths at the same time, all want to access this loopback port. If you modify it, it will also affect many roads. To be honest. In fact, it doesn't matter which one you change. Let's change the physical port first. I wish I went down now. Increase the cost above. So which interface can I change? Let's just pick an interface. Since I said it, this is a loopback port. Then this interface and this interface. Let's change the device in the middle. For example, I changed the interface of R4 to a larger size. Because routing is converged like this. So it goes under this interface. I make it bigger. It is now 10. I changed it to 100. I just make it bigger. So we go into the R4 device. Interface E01. IP OSPF cost 100. Then we look at this route. If R1 goes to 2.2 now, it seems that there is only one jump. The next hop just now seems to have 2 hops. Now there is only one left in this list. Then it means that when the data passes, it goes down. Because it checks the routing table forwarding. This is the one in the routing table. It matches this one. Then come back and hope it goes on. Which is also equal. For the top. The packet was destined for R1 when it passed. Routing is converged like this. I hope to make the above road bigger. When replying to the packet. Hope to go on. That is. When the packet comes back. Make the road below bigger. Then for R1. Routing is converged like this. For R2. This is how routing converges. If you want to make the cost of the path R2 larger, I should change these interfaces. The loopback port. This interface. And this interface. Since the above we changed here. Next. We will change the left interface of R3. Let's make it bigger. They are in opposite directions. We call the outgoing direction of the packet. So the direction is different. Change on R3. Interface E00. IP OSPF cost 100. Then we go to R2 to see the route to R1. Show IP route. Let me see if I changed it successfully. Haha, scared me. I thought this modification was invalid. For now. 1.1 is 2. Refresh it again. 1.1 becomes 1 article. I thought I changed the wrong interface. Okay. Not corrected. It takes time for it to work now. Just 2. Now going to 1.1 is only 24.1.1.4. Now R2 replies with the packet. The next hop is R4. It walks up. So, when data is being sent, you will find. This is how the traffic goes. The return traffic goes like this. Fulfilled this requirement. Now the last one left. We now want to telnet it. Let's configure telnet first. That is, I can telnet this 2.2 on this 1.1. Then we first enable the telnet function on R2. Set user. VTY04. Up to 5 users can log in. Then we still set a password. Password Cisco. One way we'll set it up later. Transport input telnet. OK. Set up. Telnet function is enabled. After opening. Let's test whether we can telnet on R1. Telnet 2.2.2.2. Password Cisco. We climbed up. It is possible to telnet. We exit. Now the last one left. Can telnet but not ping. It's actually a ping. You might say. We don't know exactly how to filter. Beginners often fall into a dilemma. When an ACL is configured. When you can't get rid of some traffic. Just configure one more. At last. A lot of rules may be entered in an ACL. Finally killed it. But I don't know which one works. Many students do this when they are beginners. It is recommended that if you are trying it out for the first time, get rid of the previous one. Then enter the new. See which one works. It is recommended that you enter an ACL in R3. Then go to Filter. Filter ICMP traffic from this 1.1 to 2.2. We actually talked about this just now. In fact, it's okay for you to do it in R2. But we're usually as close to this message as possible. Don't be the last to do it. Do it before. But I tell you, you can't do it here in R1. Because a device cannot filter out the traffic generated by itself. So you guys don't do it on this device. You can choose the left interface of R2. Or the left interface of R3. Because the traffic that comes from it is bound to go down. Your configuration above is useless. This device data will be initiated by R1 later. Let's take a look at this configuration. Access list. Excuse me. I forgot to log out. Let's get out. I now enter an advanced ACL. Because we now want to match it exactly. Access list 100. Deny current ICMP traffic. From a host 1.1.1.1. Reach another host 2.2.2.2. Echo message. There is one command missing here. Access list 100 permit IP any. Don't forget this. Although today we will not demonstrate who came to visit. But this command you have to remember to enter. After configuration. The interface has not been called yet. Call the left interface of R3. Interface E00. Enter this interface. Then we call IP access group 100 in. Then press enter. Now we are done. So now we can do a demo. First check if you can ping here. Secondly, see if you can telnet. Let's look at ping first. Because we have now isolated the ICMP message. Actually, now it should be unable to ping. That is, I am now on R1 to ping R2. If so, can ping link A? It definitely works now. Because when the data goes out now, if you do not specify the source, it is the outgoing interface. So it's definitely 02 now. 13.1.1.0. Send message to R2. R2 replies with packets back to this interface. It has this route. There is no strategy for this route. Then it can reply packets. So it can be pinged. But if you add the source, it will not work. Ping 2.2 source 1.1.1.1. This doesn't work. The percentage of successful messages is 0 out of 5. None sent. I can't ping it now with 1.1 as the source. So, we test the equivalent of can't ping it, but now want to telnet it. If you telnet it directly from here, there will be problems. Telnet 2.2.2.2. You can come in too. But it's not really coming in. This is not our experimental result. In Cisco. How to specify this? How to specify from 1.1 telnet 2.2. It has some other input methods. There is an order. IP telnet source interface loopback 0. Then press enter. This sentence means, if you use the telnet function, the default source interface is this loopback port. If you do not specify the loopback port on Cisco, by default, it is still telnet with the outbound interface of the message. So if you don't set this command, go to telnet it. Its default traffic goes like this. It must be able to come. But now we want to set 1.1 to be able to telnet 2.2. But 1.1 ping fails. We have to be stricter. Although it certainly works. But I still want to emphasize. Telnet 2.2.2.2 can still come in. This is what really comes in. Telnet is a TCP-based message. It is a service on top of TCP. It is equivalent to an application layer function. ICMP is just encapsulated on top of the IP layer. It is just a 3-layer protocol. We have made a strategy for the protocol accordingly. Then you can let the data flow through this interface. It is intercepted by the ACL attached to the interface. Then this wave of message requests will not come through. The ICMP reply cannot be returned. Then the ping fails. But this is a telnet message. All other IPs are any. Other than ICMP fixed 1.1 and 2.2. Communication with some addresses such as source IP and destination IP. We released all the remaining traffic. Then once the flow is released, the result now achieved is all messages are available. Of course, telnet packets can pass through. This is our experiment. If there is something you didn't understand, you can contact my teaching assistant to get the screen recording. You can practice by yourself after class. This is our last CCNA class. Don't think this experiment is easy. Basically, all the content involved in NA is integrated. Although less equipment. But there are many functions. This is the end of our NA phase. Okay. We'll stop here. Then we also hope that students can follow us. We are ThinkMo Education. I'm Grolin Annesley from ThinkMo. I hope today's content is helpful to you. See you next class. Bye classmates.